Picture the absolute certainty of a sandcastle on a windy beach. You know, without a shadow of a doubt that the wind and waves will eventually grind that structure back into a random flat pile of sand. This is the second law of thermodynamics. The universe is a one-way street toward chaos, decay, and disorder. It is perhaps the most depressing, unbreakable rule of physics we have. But in 1944, right in the middle of a world war, perhaps the peak of human chaos, the quantum physicist Erwin Schrödinger looked at life and saw a flagrant violation of this rule. To him, a living cell wasn't just a biological curiosity, it was a physical impossibility. While the rest of the universe was rushing toward heat death and randomness, life was somehow swimming upstream, sucking order out of the environment to build complex, stable structures that lasted for decades. It drove him to a fascinating obsession. He wasn't a biologist. He didn't own a microscope or dissect frogs. Yet, sitting there with nothing but pure logic and mathematics, he made a deduction that seemed borderline clairvoyant. He argued that for life to resist this universal chaos, it must carry a specific kind of code script written on a bizarre, non-repetitive molecule he called an aperiodic crystal. What is truly chilling is that he was right. 10 years before Watson and Crick ever saw a double helix, a physicist had already ghostwritten the discovery of DNA simply by asking why life refused to follow the rules of the dead universe.
And that really does capture the sheer audacity of what he was doing. When we talk about Schrödinger's What is Life, you have to remember who he was.
Right, a Nobel laureate.
A Nobel laureate in quantum mechanics, one of the architects of the field. And he's approaching biology not as, a naturalist who loves collecting specimens, but as a hard-nosed physicist.
He sees a problem.
He sees a problem, and he issues a challenge. She basically says, look, if a cell is made of atoms, it has to obey the laws of physics, full stop. And if it looks like it's breaking those laws, then there must be some specific physical mechanism we haven't found yet that explains it.
So this was a direct assault on the idea of, what was it called? Vitalism.
Vitalism, yeah.
Yeah.
This was a really prevalent school of thought back then. It basically argued that life had some kind of special, mysterious, non-physical spark.
A life force.
A life force. An élan vital. Something that existed outside of thermodynamics and normal physics. Schrödinger's position was the complete opposite. It was the reductive view. He believed that life's machinery, even something as complex as consciousness, could ultimately be reduced to and explained by the interactions of atoms and molecules.
Okay.
And specifically by using the newest, weirdest laws of quantum theory.
So he was trying to drag biology out of this sort of philosophical mess.
And into the hard light of physics. Exactly.
Yeah.
And just by using that strict reductive logic, he makes these two actually foundational deductions. And they're really the two pillars of our deep dive today.
What were they?
First, the thermodynamic problem. Life has to, and this is his phrase, feed on negative entropy. It has to suck in order from the environment.
Okay, that's pillar one.
Pillar two is the information problem. To pass down traits, heredity requires a super stable but also super complex mechanism. And this is where he comes up with the aperiodic crystal.
Right. So our mission today is to follow those two threads.
Exactly. We want to show you how these concepts, this constant battle for order and the structure of the code that stores it, weren't just some, philosophical musings. They were the actual conceptual blueprint that led directly to the discovery of DNA.
And how they're still shaping our biggest challenges today in fields like AI and genomics.
That's the plan.
All right, so let's start with that first impossible problem, the one that makes every physicist a little anxious. The thermodynamic battle. You mentioned entropy is this inevitable march toward disorder. Let's really dig into why that rule is so ironclad and why a tiny living cell is such a massive paradox.
The second law is, I think, the most powerful law because it's not really a prescriptive law, it's a statistical one. It's just probability applied to everything.
House always wins.
The house always wins. In any large closed system, the most likely state is the most disorganized one. The classic example is, you open a bottle of perfume in a room.
It spreads out.
It will always diffuse until it's evenly distributed. It will never, ever spontaneously gather itself back into the bottle. That's the statistical tendency toward maximum disorder. And it's why the universe, left to its own devices, is heading toward what physicists call heat death.
Which is just everything being uniform and cold.
Uniform, random, and inert.
Yeah.
Yeah. A very boring place.
But the crucial point Schrödinger zeroed in on was how these incredibly reliable laws of physics they get weird when you zoom in really, really close, down to the scale of a single cell.
That is the absolute heart of the paradox, and it all revolves around the statistical nature of physics. There's a rule called the square root of n rule. It says that if you have a law based on the behavior of n atoms or molecules,
Okay.
the probable inaccuracy, the sort of wobble or deviation from that law, is proportional to 1 divided by the square root of n.
So the more things you have, the smaller the error.
Precisely. For anything you can say, a cup of tea, a planet, even a grain of sand n is an astronomical number. We're talking 10 to the power of 23 molecules or more.
So 1 over the square root of that is tiny.
It's so tiny that the laws are, for all practical purposes, perfect. We can predict exactly when the tea will cool down, and we'll be right every single time. The law is smooth and predictable.
But life isn't built on that scale.
Not at all. And this is what Schrödinger saw. A crucial part of a gene might only involve, say, 1,000 atoms, maybe even fewer.
So if n is 1,000, what does the math look like then?
Well, the square root of 1,000 is roughly 3132. So 1 divided by the square root of n is about 1 in 30.
1 in 30.
Yeah. That means the precision of the physical laws governing that little piece of a gene, like the rate of a chemical reaction or where a molecule is supposed to be, has a 3% statistical error margin.
That's huge. I mean, if my car's engine had a 3% error margin on every single piston fire, it would fall apart.
It would be wildly chaotic. Imagine an enzyme trying to lock onto a specific molecule, or a DNA polymerase trying to copy a gene. If those processes are governed by laws with that much statistical wobble, the system should be a complete mess. It should degrade into random noise almost instantly.
Yet it doesn't.
And that's the miracle. Living cells operating with these small numbers of crucial, highly organized molecules somehow maintain what he called marvelously regular and well-ordered working. They function with a precision that seems to fly in the face of statistical physics. This was the fundamental crisis for a physicist looking at biology.
So if chaos should be reigning supreme at the cellular level, how does life not only survive but maintain this incredible complexity for, 80 years? It must be getting energy from somewhere to fight back.
And that's the key. You said it. It's fighting back. The laws of entropy, the ones that say chaos always increases, they apply strictly to a closed system.
A sealed box.
A sealed box, yeah. Something that doesn't exchange matter or energy with the outside world.
But life is not a sealed box.
Life is the opposite of a sealed box. And that was Schrödinger's elegant solution. He realized life doesn't violate the second law. It just sidesteps the closed system rule by being an open system. It's constantly exchanging stuff with its environment.
So if you measure the organism plus its environment,
the total entropy always goes up. The law is satisfied. But internally, inside the organism, it can maintain its own little pocket of low entropy order.
And it does that by sucking orderliness from its environment.
That's his poetic phrase, isn't it? Sucking orderliness.
Yeah.
Or negative entropy negentropy. It's a wonderful way to describe it. Life is like an active siphon, pulling order from the universe to build itself up.
Which is just a very fancy way of describing metabolism.
It is. That's all metabolism is. The organism takes in highly ordered low-entropy structures, like a photon from the sun, which is very ordered energy, or a complex sugar molecule like glucose.
It then uses the ordered energy in that food
to rebuild its own ordered structures, to repair damage from that constant thermal bombardment, to move, to think.
But there's a cost. It has to pay the thermodynamic bill.
There's always a bill.
Yeah.
Every single action, every moment of being alive involves taking that ordered input and expelling a much larger amount of disorganized high-entropy waste.
Heat, carbon dioxide, water.
Exactly. Less complex molecules. The internal order is maintained only at the cost of massively increasing the disorder of the outside world.
So when a plant does photosynthesis, it's not just making sugar for itself. On a cosmic scale, it's a machine designed to take a concentrated, ordered sunbeam and turn it into dispersed, chaotic, high-entropy heat.
It's a machine for efficiently wasting energy. That's a perfect way to put it. And, this leads to a technical point that Schrödinger himself actually corrected later on.
Oh.
He admitted that he used the term negative entropy, mostly because it was clear and evocative for a general reader. In precise physics, especially for a system like a cell that's at a constant temperature and pressure, the more accurate term isn't raw entropy. It's something called Gibbs free energy.
Okay, Gibbs free energy. Break that down for us. Why is that the more precise term here?
So Gibbs free energy, which physicists denote as G, is basically the measure of useful work you can get out of a system at a constant temperature and pressure. Think of it as the energy's potential to do something constructive.
So when an organism eats food,
it's consuming material with high Gibbs free energy.
Yeah.
That sugar molecule is packed with the potential to do useful work. Now, in any spontaneous process, and just being alive is a constant series of spontaneous processes, the change in Gibbs free energy has to be negative. The system has to release free energy.
It has to run downhill, thermodynamically speaking.
It has to run downhill. So life maintains its highly ordered state by constantly facilitating chemical reactions that release this free energy, which is then dissipated as heat and entropy into the universe. It's that constant release of energy potential that powers the internal fight against disorder.
So, okay, whether we call it negentropy for its poetic clarity or Gibbs free energy for the physicists, the fundamental idea is the same. Life is defined by its ability to suck in ordered energy and then maximize the amount of disorder it spits back out.
That's the absolute key takeaway. And what's so fascinating is how this principle, this thermodynamic necessity, applies way beyond just carbon-based life. And this brings us right to how we're now using this idea to understand complex adaptive systems.
Like artificial intelligence.
Especially artificial intelligence.
So if a living cell is an island of order fighting against the tide of decay, then an AI is, what, an island of code fighting against the tide of universal noise?
And it's using the exact same thermodynamic playbook. There's this concept called dissipation-driven adaptation. It basically suggests that any system, whether it's a cell or a supercomputer that creates a little pocket of low entropy, a little island of order, must globally increase entropy to pay for it.
And a modern AI, one of these big generative models, is a perfect example.
It's the perfect example. There are these massive islands of computational order sitting in these huge data centers.
And just like a cell, their survival depends on consuming order and vomiting disorder.
I mean, look at the engineering and the economics of a data center. To sustain that complex computation, which is just ordered information processing, they have to constantly suck order.
Which in this case is electricity.
Massive amounts of highly ordered, low-entropy electricity. Electricity is an incredibly concentrated, ordered form of energy. And what's the main byproduct of all that computation?
Heat. Enormous amounts of heat.
Enormous amounts of chaotic, high-entropy heat. Which is why the cooling systems in these data centers aren't just an afterthought. They are the central physiological mechanism of the entire operation. They are how the AI pays its thermodynamic bill.
Without getting rid of that heat, that disorder,
the whole thing melts. The highly organized computational structures, the silicon chips, would instantly succumb to entropic chaos. The hardware fails, the computation breaks down, and all that organized information is just lost to noise.
That's an incredible parallel. The AI's internal integrity, its very existence as an organized system, is directly tied to how efficiently it can maximize disorder and dissipate it into the atmosphere.
It really elevates Schrödinger's insight, doesn't it? It goes from being a biological observation to a universal law for any kind of complexity. This general idea is that systems, and this might even include the very systems that led to the origin of life, they naturally self-organize to become better and better at absorbing energy from a source and dissipating it.
So in this worldview, life didn't just pop up as some statistical miracle.
Maybe not. Maybe life, and eventually complex computation, is simply the most efficient physical mechanism that the universe has found for maximizing entropy production in a given environment.
Life is the universe's most sophisticated radiator.
And intelligence is just a really, really effective tool for processing ordered energy and turning it into waste heat.
That is a staggering thought. The cosmic imperative is to maximize waste, and life is the perfect machine for the job.
It totally shifts your perspective. The question isn't what is life made of, but what does life do? And the answer is, it fights chaos locally by creating much more chaos globally.
Okay, so that covers how life maintains its order through time. It's constantly paying that energy bill. But now we have to move to the second, and maybe even more prophetic, deduction he made, how that order is passed down stably across generations. The information problem.
Right. We're shifting gears now from thermodynamics to, really, information theory. But the enemy is still the same. That constant, chaotic jiggling of molecules. Schrödinger realized that whatever molecule carried the genetic instructions had to solve an almost impossible physical contradiction.
Which was?
The need for both infinite variety and permanent stability.
Let's break that down. Why infinite variety?
Well, think about what it has to do. It has to store the entire blueprint, the code script as he called it, for an entire organism, a human, a fly, a piece of corn. That requires a staggering amount of information. The instructions can't be simple or repetitive. If your hereditary molecule just went AAAA, you could only specify one thing.
It has to be complex enough to spell out every single protein, every cellular process.
Exactly. But, and this is the other side of the coin, that incredibly complex, intricate structure has to be ridiculously durable. It has to have permanent stability,
It has to survive for decades inside a warm, wet, chaotic cell.
constantly being bombarded by thermal motion, and then be copied with near-perfect accuracy for thousands and thousands of generations. How on earth can a molecule be that complex and non-uniform, but also that physically tough?
Right. A gene is made of millions of atoms, each one needing to hold its exact position like a letter in a sentence. Just random heat motion should be constantly causing spelling errors, shouldn't it?
A simple, squishy, amorphous molecule would fall apart. It would lose its information in minutes. So Schrödinger knew he needed a physical structure that was inherently stable. And for a physicist, stability means one thing:
Crystals.
crystals. But that seems to create an immediate contradiction, which brings us to his truly revolutionary idea: the aperiodic crystal.
Okay, so first, what's a normal periodic crystal?
A periodic crystal, think of salt, or a diamond, is incredibly stable for one reason. Its atoms are locked into a simple, repeating, rigid lattice. The pattern is uniform and redundant.
He called it a repetitive wallpaper pattern.
That's the perfect analogy. Once you know the pattern in one tiny square of the wallpaper, you know the pattern for the entire wall. It maximizes stability, but it contains almost zero information. It's the ultimate stable structure, but it's also the ultimate blank slate.
So he needed something with the physical toughness of a crystal, but without the boring repetition.
Yes. He proposed the aperiodic crystal. It was a conceptual leap. He imagined a molecule that had the physical stability of a crystal. Its atoms held together by incredibly strong, durable Heitler-London covalent bonds, which are the strongest chemical bonds. But, and this is the whole game, its internal structure was non-repetitive.
So instead of AAA,
You get a long chain that goes, say, ATCGGZ. The links in the chain are strong and stable, like in a crystal, but the sequence of the links is highly variable. It's not a repeating pattern.
the Raphael tapestry analogy.
Exactly. The tapestry is an elaborate, meaningful design where every single stitch, or in this case, every single atom or group of atoms, plays a unique, irreplaceable informational role. That non-repetition, that aperiodicity, is what gives it a massive capacity for storing information.
And he actually did the math on this, right in the book.
He did. He showed that if you build a chain using just 25 different letters or subunits, you can create an astronomical number of combinations. He made the problem of storing the blueprint of life go from being inconceivable to being mathematically plausible. He gave the code script a potential physical home.
This is really the moment where physics hands biology a treasure map. But the stability question is still bugging me. How does quantum mechanics actually lock these complicated atoms in place so they don't just jiggle loose from all that heat?
And that is where quantum theory provides the necessary miracle. According to quantum mechanics, a molecule can't just exist in any old random configuration. It can only exist in a discrete set of stable states. Think of them as energy levels, like steps on a staircase. You can be on step 1 or step 2, but you can't be halfway between them.
Okay.
So a molecule sitting in one of those states, say the configuration that correctly codes for blue eyes, is inherently stable. To change its configuration, to move a single atom, what's called an isomerism.
It can't happen gradually.
It can't happen gradually. It has to happen all at once in a quantum jump.
And to make that jump, you need a big push of energy. You have to get over some kind of energy threshold.
Exactly. Like pushing a boulder out of a deep valley, you have to push it all the way up and over the hill to get to the next valley. The energy needed to get over that hill is the threshold energy, which Schrödinger called W.
And as long as the random heat energy of the cell, which he called KT, is much lower than W.
The molecule is locked in, it's safe in its valley, the gene is stable.
So the stability of a normal, healthy gene, a wild-type gene, is just a gene that happens to be sitting in a very, very deep energy valley.
That is the physical mechanism of permanence. And this is also how he brilliantly explained the nature of spontaneous mutation.
A mutation is a quantum jump.
A mutation is one of those rare, discontinuous quantum jumps. It happens when, just by pure chance, a random fluctuation of thermal energy, the chaotic jiggling, provides just enough of a kick to push that boulder over the energy hill, WTF, into a new, stable, but potentially incorrect configuration.
I have to stop you there. This is wild. He is taking the most abstract, bizarre, counterintuitive idea from quantum physics, these sudden jumps, and applying it directly to the most fundamental process in all of biology. People just like, what is this guy talking about?
Oh, it was absolutely radical. For biologists who were used to seeing gradual, continuous change, this idea of sudden, discrete jumps dictated by invisible energy thresholds was Well, it was out there. But for physicists, it was incredibly compelling. It provided a concrete physical reason for stability in a world that should be chaotic. It was audacious, and that's what made it so powerful.
And the math behind it is incredibly sensitive, right? That relationship between the expected time for a mutation and the ratio of that energy threshold, W, to the heat energy, KT.
It's astonishingly exponentially sensitive. The formula he uses shows that the average time you have to wait for a mutation, T, depends exponentially on that ratio, W divided by KT.
Let's put some numbers on that.
Okay, so if the ratio W over KT is, say, 50, meaning the energy hill is 50 times higher than the average thermal kick, the expected lifetime of that molecular state might be about 16 months.
So a very unstable gene, a mutant.
A highly unstable mutant, yeah. But now, let's say evolution tweaks things just a tiny bit and makes that energy valley just a little deeper. The ratio goes from 50 up to 60. The expected lifetime for that gene to mutate doesn't just increase a little bit. It jumps exponentially to 30,000 years.
Wow.
A tiny increase in the energy threshold provides a nearly miraculous increase in permanence.
And that explains everything about why life is so robust. The genes that work, the wild-type genes, have been selected over eons precisely because they exist in those super deep energy valleys that require a massive push to change.
And this wasn't just a theory he cooked up. It was strongly supported by the genetic experiments of the time, especially the work on radiation and X-rays.
How so?
Well, experiments had shown that the rate of mutation was directly proportional to the dose of X-rays you blasted something with. That strongly suggests that a mutation is a single, localized, high-energy event. A single X-ray particle comes in, delivers a high-energy kick of about 30 electron volts right near the gene, provides the necessary energy W, and triggers that quantum jump. Schrödinger provided the physics equation for biological inheritance.
So he basically reframed the entire question of heredity. He took it from the realm of, what shape is the cell, to what is the information density and quantum stability of the hereditary molecule.
He reduced a fuzzy biological observation to a quantifiable physical probability. And more importantly, he gave scientists a search criterion. He told the world what they should be looking for: something stable, covalently bonded, information dense, and non-repetitive.
Which brings us to the historical tipping point. This little book, published in 1944, becomes one of the greatest recruiting pamphlets ever written.
It really was a call to arms. You have to remember the context. It's the end of the war, and you have all these brilliant physicists who've just seen their work used for incredible destruction. They're looking for a new, profound, and maybe more positive riddle to solve. And Schrödinger basically translates the problem of life into their language, the language of information and code.
He makes it a physics problem.
He makes it a physics problem. He draws a line in the sand and says, genes are not some mystical life fluid. They're physical code scripts. Now go find them.
So let's track that influence. Let's look at the actual giants who went on to solve the structure of DNA.
The chain of influence is just undeniable. It's a perfect case study in how a powerful idea can reshape a whole field. You start with James Watson.
Okay.
He reads What is Life? While he's a PhD student, and he later describes it as an almost instant epiphany. The book convinces him of two things. One, the gene is a molecule with a definite structure. And two, that structure can be found using the tools of physics, specifically X-ray diffraction.
So it sets him on his path.
It completely pivots his career. He becomes obsessed with finding the structure.
And what about Francis Crick?
Crick's story is a little different. He was working in military research. He said he was initially somewhat less impressed by the book's more philosophical arguments, but he was deeply influenced by the sheer intellectual force of a physicist like Schrödinger taking biology seriously.
It legitimized the field for him.
It did. It motivated him to leave military research and start investigating the three-dimensional structure of large biological molecules. Initially, he was focused on proteins because that was the leading candidate for the genetic material at the time.
But after the discovery of DNA structure?
After the discovery in 1953, Crick actually wrote a letter to Schrödinger. And he acknowledged his debt, saying that the term aperiodic crystal was, and this is a quote, very apt for describing the DNA molecule.
So Schrödinger gave them the concept of the structure, even if he didn't know what it was made of. And that brings us to Maurice Wilkins.
Right. We can't forget Wilkins, who was working with Rosalind Franklin and got those crucial X-ray pictures of DNA. Wilkins was directly inspired by the aperiodic crystal idea. He was expert in the physics of crystals, both perfect and irregular ones. Schrödinger basically gave him the intellectual vocabulary he needed to interpret the strange diffraction patterns he was seeing from DNA. He was looking for a crystal that wasn't periodic.
The coordination of it all is just breathtaking. But you mentioned there's this incredible coincidence around the timing of the book's publication.
It is uncanny. So Schrödinger gives the lectures that become the book in 1943. The book is published in 1944. Meanwhile, in May of 1943, completely independently, another crucial piece of the puzzle falls into place.
What was that?
A scientist named Oswald Avery, along with his colleagues, publishes the definitive results from his experiments, proving that DNA, not protein, was the actual substance that carried hereditary information.
So wait, Schrödinger logically deduces what the instruction manual must look like, a durable, complex, aperiodic code.
And at the exact same time, Avery experimentally identifies the physical book itself, DNA.
The stage was perfectly set. The theoretical blueprint gets published just as the experimental target is identified.
All that was left was for this new generation of physicists turned biologists, like Watson and Crick, to take that conceptual map and find the physical structure. And the double helix, with its non-repeating sequence of nucleotide bases locked into this incredibly stable crystalline-like structure, it was the perfect physical realization of the aperiodic crystal.
And if we jump forward to today, the idea of the code script isn't just some historical curiosity. It's the operating manual for our most advanced biological technology.
Absolutely. The ultimate fulfillment of that code script idea is, of course, genome editing, specifically CRISPR-Cas9.
Jennifer Doudna's work.
Exactly. When scientists use CRISPR, they are working from the fundamental assumption that life is information written on a discrete, editable code. CRISPR is basically a pair of molecular scissors guided by a piece of RNA that can find a precise spot in the genetic sequence and make a cut. It's a programmable tool that lets you change the code of life with the precision only dreamed of.
We are literally debugging the operating system of life. And that kind of power, it has to fundamentally change the conversation around what life even is.
It has to. Schrödinger's reductive view that life is just physics and information is what delivered this incredible power. But that power opens up some really profound philosophical challenges, especially when we start looking at the brain and the body as just another type of complex computing system.
Okay, so let's follow that thread. Let's take the idea of code and order into modern neuroscience. We talked about how a data center fights entropy, but how does the brain fight entropy? And this is where the free energy principle comes in.
The free energy principle, or FEP, is probably one of the most comprehensive theories in neuroscience today. And it is a direct intellectual descendant of that thermodynamic fight against chaos that Schrödinger identified. FEP, which was mostly developed by Carl Friston, basically proposes that any living system, especially a brain, is fundamentally a hierarchical generative model.
Okay, that's a mouthful.
It is. But the core purpose is simple. Its main job is to resist disorder by constantly trying to minimize prediction error, or, as he calls it, surprise.
And surprise is just unexpected stuff happening, is high entropy input from the world.
That's it, exactly. The environment is inherently chaotic and unpredictable. If the world keeps surprising you, it means your internal model of reality is wrong. It's breaking down. And that's a form of internal disorder. To survive, you have to maintain an ordered, predictive model of the world.
So how does the brain do that?
It's constantly generating hypotheses or predictions about the sensory input it expects to get. Then the real sensory input comes in, light, sound, whatever. The brain calculates the difference between what it expected and what it got. That difference is the prediction error.
And its whole job is to make that error as small as possible.
Right. And it can do that in two ways. First, it can adjust its internal model, that's prediction or learning. It refines its model so it makes a better prediction next time.
Okay. And the second way?
The second way is to actively change the world to make the sensory input match your prediction. That's action. If your brain predicts that your hand is holding a coffee cup, but the sensory input says it's empty space, that's a big prediction error. So you minimize the error by moving your hand to grab the cup.
So the ancient thermodynamic fight against entropy has now become an informational fight against surprise.
It's the ultimate expression of sucking order from the environment. The process of minimizing prediction error is functionally the same as minimizing the overall disorder of the system. The brain is fighting to maintain its ordered model of reality against a constant storm of sensory chaos.
And the FEP model explains how this happens at different speeds on different timescales.
Yes, and the different timescales are crucial. On the very fast timescale, milliseconds, you have just raw neuronal activity. Your neurons are firing constantly to make rapid inferences about what's happening right now. A shadow moves in your peripheral vision, and your neurons fire instantly to update the model and minimize that immediate surprise.
That's perception.
That's perception. Then, on the slower timescales, seconds, minutes, even decades, you have changes in how your neurons are connected. The synaptic efficacy. This is long-term learning and memory. It's how the brain encodes the deep causal structure of the environment.
So the slow changes provide the context for the fast ones.
Exactly. The brain self-organizes to suppress prediction error all the way up and down this hierarchy. A high-level belief, like I am safe in my own house, can suppress a prediction error at a lower sensory level, like, why did the refrigerator just make a weird noise? The brain says, don't worry, that's normal, my model is still correct.
So our sense of self, our memories, our identity, it's all just the long-term low entropy result of this massive nonstop prediction machine.
It's the most sophisticated example we know of a system that actively takes in chaotic input and forces it into a state of order that is based on its own internal order. Whether it's a single cell burning sugar to dissipate heat, or a human brain minimizing informational surprise, the underlying thermodynamic imperative that Schrödinger pointed to is identical: survive by exporting disorder.
But this reductive view that life and mind are just code and information, it really forces the question of the boundary, doesn't it? The boundary between carbon-based life and silicon-based life. If it's all just about fighting entropy, what actually makes life or consciousness special?
That is the philosophical chasm that Schrödinger's work opened up.
Yeah.
And it's why it's so incredibly relevant now with the rise of advanced AI. If any complex adaptive system, regardless of whether it's made of meat or silicon, follows the same fundamental rules: store information, fight entropy, minimize surprise, then the specialness of carbon-based life starts to look a bit shaky.
I mean, when we search for life on other planets, what are we looking for?
We're looking for chemical imbalances. We're looking for ordered states that shouldn't exist naturally according to the normal rules of chemistry and physics. We are literally searching the galaxy for pockets of planetary scale negentropy. If that's the universal definition, then where does the self, the I, actually live?
And what's so fascinating is that Schrödinger himself, the man who gave us the physical basis for this reductionism, he seemed to resist the idea that consciousness was just a side effect of atoms.
He wrestled with it deeply. If you read the final chapter of What is Life, he leans heavily into a kind of monist philosophy, particularly the ancient Indian thought of Vedanta.
Right.
He says that while the physical organization of the brain has to be highly ordered to produce orderly thought, he asserts that consciousness itself is singular and eternal. It exists outside the physical world that science describes.
He said the purely materialist picture was ghastly silent about everything that really matters to us.
He did. He believed the mind itself did not belong to the world of energy. He even used the Sanskrit phrase, tat famasi, this is you, to suggest that the idea that we are all separate individual consciousnesses is just an illusion, that the I is not just a part of existence, but in some sense, it's the whole thing.
It's a really powerful intellectual hedge. He gives us the complete blueprint for the physical machine, but then insists the driver is somewhere else entirely.
And it's a critical warning for us today. Just because we can show that the body is a complex physical code that obeys physical laws, that doesn't automatically answer the profound questions of identity or mind. The code is just the physical basis for the inheritance of organization.
But the very success of his reductive view forces us right into the middle of the highest stakes ethical debate of our time.
It does. Which brings us to the profound power and, frankly, the vertigo that comes with being able to edit the code script ourselves with tools like CRISPR.
Yeah, that vertigo is real.
When you talk about scientists using CRISPR-Cas9, you're talking about the ultimate expression of the code script idea. The vertigo comes when you realize we now have the power to debug the operating system of humanity itself. When a scientist can look at a genetic sequence A, T, C, G, and know they can go in and chemically replace a single one of those letters with precision, the line between natural creation and human computation it dissolves.
And the immediate applications are huge. I mean, CRISPR is already being used to treat horrible genetic diseases.
It is. It's in clinical trials, offering real hope for things like sickle cell anemia by editing the DNA of somatic cells. That is, non-heritable cells.
But the ethical red line, the point of no return, is when we talk about applying that power to the human germline.
Exactly. Germline editing means making changes to human DNA that are heritable, changes that will be passed down to all future generations. Schrödinger argued that the durability of life rests on its code script. Now we have the tools to rewrite the terms of that durability.
And that forces us to completely reevaluate what biological identity even means. If we can control the blueprint, What's the difference between curing a disease and enhancing a trait?
The discussion is no longer theoretical, is it? It's about making permanent, irreversible, heritable changes to the human code.
So the core of the ethical problem is defining the line between what we're allowed to fix and what we're allowed to create once we start treating life as just a piece of editable code.
That's the whole thing. Jennifer Doudna and many others in the scientific community have been screaming from the rooftops about the need for extreme caution and global consensus on this.
Yeah.
Because Schrödinger gave us the intellectual framework that life is a durable, readable, and therefore editable code, the global community now has to bear the immense existential responsibility of deciding who gets to be the editor and what the rules are. It's the ultimate ethical dilemma, and it stems directly from a physicist's pure logical deduction almost 80 years ago.
It really is the ultimate expression of both the promise and the peril that was baked into Schrödinger's original hypothesis. He told us that life is information and order fighting chaos, and now we are asking who gets to write the code for tomorrow.
And the sheer power of that logical deduction is what makes this story so compelling. You have Schrödinger, a physicist who, as you said, didn't dissect frogs, providing the conceptual blueprint for arguably the greatest biological discovery of the 20th century. He established the two irreducible pillars that all of modern life science is built on.
Let's recap them one last time.
First, life is an open thermodynamic system. It has to actively import order, or Gibbs free energy, to delay its own inevitable decay. And that principle applies to all complex systems, from a single cell to an AI.
And
Second, heredity is written in a complex, durable physical code, the aperiodic crystal, and its structure is maintained by the strict rules of quantum mechanics, only changing through those rare, discontinuous quantum jumps we call mutations.
Thermodynamics and information theory.
Those two concepts, they form the bedrock that finally unified physics and biology, and they're still driving the most advanced research in the 21st century.
And it all started with a simple question asked during a time of immense global chaos. Why doesn't life follow the rules of the dead universe? The elegance of his thought unified statistical mechanics, quantum theory, information science, and philosophy all in one small book. It remains an enduring testament to the sheer power of disciplined, imaginative logic.